Thank you for the invitation. In my abstract, I had two subjects. One of which, but when I was preparing my talk, I decided, in a half an hour, I don't really have time to discuss both. So, if you forgive me, I'm just going to talk about the second subject, which is something about harmonic functions, and the other subject, which was reconstructing a network from boundary observations, will have to wait for another day. So, the title is "Can you see the sound of a drum?" This is there's a famous paper of Mark Katz. Can you hear the sound? Sorry, what did I say? Yeah. Can you hear the shape of a drum? Right? I mean, of course, you can see the shape of a drum, and you can hear the sound of a drum. So you might as well ask the fourth question, which is, can you see the sound of a drum? And I have to tell you what that means. And so for the first 3/4 of the talk, we'll be doing some geometry. I hope that's okay in this audience. But some elementary Euclidean geometry at most. So hopefully you'll appreciate it. And we'll get to some random stuff at the end. So let's see. So first, let me just tell you what a harmonic function is. Probably everybody knows, but if we're talking about a two-dimensional harmonic function on R2, right? A function is, what does it mean to be harmonic? It means that the Laplacian is 0. The Laplacian for a smooth, C2 function is just the second derivative of x plus second derivative of y. And this is your standard two-dimensional harmonic function, this potato chip function, and or I should say crisp. Sorry, x squared minus y squared, and it has this nice property, this sort of magic property of harmonic function is that you take any point, the average of the value of the function on any concentric circle around that point is the value at the center. Right? This is not at all obvious from this formula, but it's something you prove in your complex analysis class, something like that. On a graph, a function, so now we have a function on the vertices, and let's just stick with real valued functions. It's going to be harmonic if the value at any vertex is the average of the value at its neighbors. All right, and one way to write that is you sum over all neighbors w of v, f of v minus f of w, you get 0. So, right, this is not new to anybody here. Right, right. Think of a spider web. Think of it as a graph. Each vertex, each place where the webs cross, is a spider web is under tension. So every point is being pulled toward the four neighbors, and the fact that each point is not moving is an equilibrium condition that says that the sum of those four forces, or however many forces there are, is 0. And so if you think about what it means in terms of forces, if you this equation f of v minus f of w is a think of it as a sort of, in the spider web, which is sort of a two-dimensional harmonic function, as a vector pulling the strand of the spider web in this direction, and there's these four vectors, and they balance. So they sum up, they add up to 0. There are lots of ways to think about harmonic functions. Here's one of my favorites. It makes a pretty picture. If you have a square tiling in the plane, and you look at the y coordinates of the horizontal segments, right? There's this horizontal segment, and it's got 4 squares around it, 2 above and 2 below. The y coordinate here is the average of the y coordinates of the other horizontal segments across the squares. So this segment has sort of 4 neighbors, right? One segment here, one here, one here, and one here, and its y coordinate is the average of those. And the reason it's the average, is because that equation, right? It's not right. This difference f of v minus f of w is the same as this length because it's a square. this distance is the same as that distance. And so, when I take the sum of f of v minus f of w, I get two negative values for the above squares and two positive values for the lower squares. But the sum of the above, the negative values is the length, and the sum of the positive values is the length, and those cancel. Was that too fast? No? That was okay? It's trivial, yeah. Okay, good. Trivial for Bela. Okay, well, let's go back to spiderwebs. By a spiderweb, I just mean a spring embedding of the graph. So you take your planar graph. All my graphs are going to be planar in this talk. You pin it at some outer boundary vertices, like these four outer boundary vertices. I pin it to some frame, right? Think of it like a tennis racket or something. And on each edge, there's a spring, right, which in equilibrium is sort of very short. So the Hooke's law for a spring says that the force of the spring is proportional to the length. Right? The more you pull the spring, the stronger it's pulling back. And when you let the graph come to equilibrium, there's some equilibrium shape in which every point is being pulled towards its neighbors by a certain force. And the direction of the force is, of course, the direction of the edge. And the strength of the force is well, depends on the spring constant. Well, but let's, if all the springs have the same spring constant, they're all the same manufacturer springs, then you'll see that the x and y coordinates are going to be harmonic functions. Okay, but that is for each vertex, you look at its x coordinate, it's the average of the x coordinates of its neighbors. And same thing for the y coordinates. Right? For the same reason that this vector plus that vector add up to 0. So I have a little, yeah. If you look at these three vectors, they have to sum to 0 because that point is not moving. Right? There's no the net force is 0. Therefore, the x coordinate of this vector plus the x displacement of these three vectors has to be 0. So it's harmonic. Okay, so that's what a spiderweb is, and of course, a simple generalization is to use springs with different constants, right? We're talking about, networks, not just graphs. So here, the weight of an edge now is going to be a positive real number, which is the stiffness constant of the spring. Okay, and Hooke's law in this setting says that the force is that constant times the length of the spring of the edge, right? So now. In this network setting, we have a slightly different notion of a harmonic function, but the function is harmonic if the sum of the values f of, so this is the same sum over all neighbors w of a vertex v, f of v minus f of w times the spring constant is 0. And these spring constants are of course symmetric, right? There's one spring for an edge, the amount of pull from one direction is the same as the amount of pull from the other direction, so you get this symmetry here. Please feel free to ask questions if I'm going too fast or too slow, or shall I speed up? Okay, so here's some very simple questions. What spider webs are possible, and can one reconstruct, if I show you a picture of a spider web, can you reconstruct the spring constants? Here's an example. Right, I'm drawing this planar graph. I've pinned it to 3 points, tacked it down to the screen. But these 3 points are sort of free to vary, and I put some. There's some spring constants which I'm not showing you here. Well, first of all, there's 6 edges here. So there's 6 parameters I can throw in this problem, one for each edge, one spring constant for each edge. But if I multiply all the spring constants by the same amount, by 2, if I double each spring, the configuration won't change. Right? There's some scale invariance. If I multiply all the weights by a constant, the image won't change. The equilibrium position won't change. which cuts it down to a 5-dimensional space of graphs, right? On the other hand, there's a 6-dimensional space of embeddings of pictures of this type, right? Because I can wiggle each vertex in 2 dimensions of freedom for each vertex. So you have to ask yourself. So from a geometric point of view, one can ask which configurations of 3 points here are going to arise from a spring embedding of a graph, and which ones are not. Right? Does everybody understand the question? Let me, oops, that's not the right file. There we are. I'll show you the picture. Can everybody see this one? Make that bigger. No, that didn't work. Okay, so here you see that, well, it's the same picture. And I've got these six sliders which control the spring constants. And so I can move around in the space of these triangular spider webs by adjusting the spring constants on the 6 edges. And so what's the condition on these 3 points which makes it arise from which makes it harmonic? Anybody?
Out of 6 on your equation.
Sorry?
What you said before, the forces cancel out in x and y, so it looks like you can reconstruct this whenever it's 3 regular.
Whenever it's 3 regular?
Yeah.
Oh, well, yeah, but I'm asking a different, I don't want to reconstruct it, I just want to know when, for which triples of points in here does it arise from a spring embedding?
Oh, what's the poly?
Oh, okay, here's the answer. If you draw the line, this is just an answer for this particular graph, and then we'll generalize it in a second. If you extend the line, these 3 lines, they have to be concurrent. So it's kind of a fun, a cute little geometric description of the set of spider webs, and you can certainly check, once I draw those lines in, as I move the spring constants around, those lines stay concurrent. If the lines were not concurrent, then there would be some sort of torque to the triangle. It would try to rotate. So if you want some sort of physical meaning for the concurrency, that's what I learned from John Sullivan. All right, let's go back. So here's a slightly larger graph here. Again, I've got now I've got 8 edges. So I've got the same problem as before, because up to scale I've only got 7 variables, but I've got 8 sort of positions of the vertices, and can I tell? How do I tell whether it's coming from a harmonic function? And so let me just go through one method to tell that. If it were harmonic, then at each vertex is of course being pulled towards its neighbors with some forces which we can't see from the picture, but we know at least the directions of those forces. We don't know how strong they are because we don't know the spring constants. I'm not showing you the spring constants. I'm just showing you the actual positions, equilibrium positions of the vertices. But since the force is balanced, that is, the sum of these 3 vectors is 0, right? What I can do is just rotate those vectors by 90 degrees, and they will, sum to 0. They make a triangle. So one way, so here's how you tell. Here's one sort of algorithm to detect this harmonicity, is you take all the edge vectors and turn them by 90 degrees, right? So they're draw these perpendicular segments, and then at each vertex here, each vertex happens to have degree 3 in this example. You know what the force has to be, in this direction. So the perpendicular force is like that. But since the force is balanced, you have to be able to make triangles out of these edge directions. And if you know the directions of a triangle, then you know the triangle up to scale. So from these perpendicular segments, you can scale them up or down appropriately so that they form these little triangles. At least at each vertex, you form these triangles. And, you know, you move them to the center, move them to a common vertex, and then you have to rescale those triangles so that they fit together. So if the triangles fit together, then it was a harmonic embedding. And if they don't, if it's something like this, then it's not harmonic. So what goes on here? If you look at that first vertex here, right? I know the perpendicular edges, so I can make a triangle by adjusting their lengths to make a triangle. So let me fix this triangle. Then I can adjust the lengths of these three perpendiculars to make a triangle, and I scale it so that these two sides agree. And then I do the same thing with the next triangle and the next triangle, always making the new side agree with the side from the previous one. But when I get around that face, it may or may not be the case that this last edge, has the same length as the edge I started with, and that's the one-dimensional condition for harmonicity. So the theorem, which I essentially proved for you, an embedding of a graph that is a spider web of this type is going to be harmonic if and only if you can draw a dual graph where the edges are all perpendicular to the original graph. Kind of like in this example, right? Each blue edge, this blue graph is a dual to the original graph, and it is a planar dual, and each edge in the blue graph is perpendicular to the corresponding edge in the original graph. Okay, so that's the necessary and sufficient condition for the original graph being harmonic with some spring constants. Okay, so now we can come to the problem of the title. Can you see the sound of a drum? And when you look at it, if I show you this picture, right, and I ask you what does the drum sound like when you beat on it, it depends on a lot of things, right? When you stretch a membrane over a frame, right, you can stretch it, more tightly in certain directions than others. Maybe I should draw this picture here. Suppose I have this piece of rubber material. Here's my frame of my drum, and I've got a piece of rubber material, and just so that we can sort of see what's going on, I put a little grid on that rubber material, and then I stretch it over my frame. And when I stretch it, of course, these grid lines give some sort of grid lines on my frame, and depending, I have some choices here about stretching it tighter in this direction or that direction, and those choices will affect the sound of the drum. So I want to know whether I can tell what the sound is by just looking at the image of the grid lines. So what I see is of course an embedding of a graph, of a planar graph, with some forces. So let's pretend like everything is discrete. Okay, it's a discrete drum, and I want to know if I can reconstruct the spring constants. So the reconstruction of the spring constants, if I can do that, then I will know what the forces are, and I will be able to reconstruct the sound. When you hit a drum, right, the sound that you hear is related to the spectrum of the Laplacian operator. And once you know the spring constants, then you know what the Laplacian operator is. You can, by some linear algebra, reconstruct the spectrum. So the sound of the drum is really related to these spring constants. Right, so that's the relation between the two questions. All right, and as we saw, if you want to reconstruct the spring constants, we saw an algorithm to detect if the thing actually is a drum, if it's a real spider web. But now we want to know whether the reconstruction is unique. So we sort of did the existence problem. We want to know the uniqueness of the reconstruction. If I have a graph like this, this is another spider web in equilibrium. Can I detect the forces up to, let's say, up to a global scale? Right? If everything is stretched, uniformly by some factor, then I won't be able to tell that from the diagram. But let's ignore the global scale. And so here, let me show you a picture. In this case, the question of reconstructing the spring constants has to do with is there an essentially unique up to scale dual graph with perpendicular edges? And I think you can see from this simulation here that here's a whole family of dual graphs for this spider web, which are all different from each other, and therefore the reconstruction problem doesn't have a unique solution for this particular graph. In fact, our algorithm before showed that the reconstruction problem is possible if the graph is trivalent, but it's not true in general. And here's sort of just a counterexample. If your graph contains, suppose your picture contains an equilateral triangle like this with this y in the middle, then I can take those. I could take this whatever solution I have for the spring constants, and if I add x to the outer these three edges and subtract 3x from those two edges, then each spring is so the springs are getting stiffer on the outer boundary and weaker on the inner ones. But the net effect is that the force in this direction is increasing by x, in that direction it's increasing by x, and in that direction it's decreasing by 3x, and those things make no effect. The sum of those three vectors is 0, so that the net force on this vertex is not moving when I make that small change. So this is a sort of a counterexample to the uniqueness of the reconstruction problem for the forces. So it's just a sort of a local, you can make a local change to the forces without changing the position of the vertices. Does that make sense? Okay. 5 minutes, okay. As long as we're talking about harmonic embeddings, there's a more general class of embeddings which are called convex embeddings, so of a planar graph. So let's just say an embedding is convex if the faces are convex polygons, right? Like this example. So you take your planar graph, you pin the vertices, and then you want the faces to be convex. And well, it's not hard to prove that the space of convex embeddings of a graph, of a planar graph with pin boundary, is actually homeomorphic to topologically it's just a ball, r to the 2v, an open ball. And for a trivalent graph, that's sort of the easiest case. You could see this by using barycentric coordinates, right? Each vertex, if it's a convex embedding, then each vertex, if it's degree 3, has to lie in the convex hull of its three neighbors. And the convex hull of the three neighbors is a triangle, and you can parameterize that triangle with the standard triangle, and so this vertex is, if you use barycentric coordinates, then you can describe this vertex uniquely by the position it sits at in that triangle. It's a convex combination of its neighbors. And right, so for each vertex you have essentially 2 barycentric coordinates. Well, you have 3, but their sum is 1, and that gives a parameterization of the space of convex embeddings. And it's not hard to show that every set of barycentric coordinates is actually realized by a convex embedding. Okay, so this allows us to do some probability. If we take a large planar graph like this, honeycomb, and let me just pin all the vertices on the boundary, and if I do that, well, in a standard embedding, every vertex has barycentric coordinates 1/3 with respect to all its neighbors. It's in the center of the triangle formed by its neighbors. But if I change those barycentric coordinates to some arbitrary things, then the natural choice is to just choose IID so a natural probability on the set of convex embeddings is obtained by choosing these barycentric coordinates. Well, I call them transition probabilities because they're transition probabilities for the random walk. Just choose them IID in the triangle for each vertex. When you do that, you get a new embedding of the graph, random embedding of the graph, and well, the theorem says that as you vary these transition probabilities, you get all possible embedding, all possible convex embeddings, and this is a natural Lebesgue measure on the space of all possible embeddings. And one can ask, from a probabilistic point of view, what does it look like? Well, is there some limit shape? And let me just sort of finish here. If I compare this with a random harmonic embedding, a harmonic embedding is a special case of the random convex embedding. So here, for example, if I take just conductances, IID random, then a harmonic embedding is sort of very smooth. A vertex does not move very far from its original position. I mean, the distance it moves is little o of the system size. Whereas it's an open question in this case, how far does a vertex move from its equilibrium condition for this random convex embedding? And from the picture, it looks like it moves a long way. And from simulations I've done, it looks like there's no sort of scaling, there's no non-random limit shape. On the other hand, if you talk to Ofer Zaitouni, who has, is more of an expert on these things, he says that there actually is, he conjectures that there is a limit shape for this thing. So you just go to extremely large system size, then things will settle down. So we kind of disagree at that point. But yeah, here's another simulation. So, okay, I don't really have time to talk about that, but that was one of the last. I'll just show you the picture, and I will stop here. Thank you.
We have time for some questions.
Ridiculously beautiful results, but and even your classical result, which should have been proved 150 years ago, or 200, even that's new. They were describing which one is realizable.
I have not found it, but I would think that I'm sure somebody has done it, but I don't. People haven't really thought about networks. People think about random graphs and harmonic functions on graphs, but nobody. Seems like very few people want to change the conductances and or spring constants and deal with that case. So it's possible that's new, but
absolutely wonderful.
I have not found it. Yes,
I have a question. I've seen a whole bunch of different definitions of graph Laplacians. This is the first time I've seen a physical interpretation of it. Are you familiar with the other graph Laplacians, and do they have physical
other graph Laplacians? No, there's only one graph Laplacian.
Okay.
I know several different ways to define the same object, but there's just one that I've ever encountered that makes any sense. It's a linear operator, d star if you want, but
Okay.
How do you define a graph
I've
Laplacian?
seen one that you put an inverse weight on the degree of the node. We can talk
Yes.
offline.
Yeah, that's the same one.
Okay.
It appears in various guises, but it's the same.
Okay. All right. Other questions we can reserve for the coffee break. Let's thank Richard one more time.